Okay, let's talk about polynomial functions. So it turns out we've seen a lot of polynomial functions already, and maybe we just didn't recognize them as such. So linear functions, lines, they're polynomial. Quadratic functions, parabolas, those are polynomials. So a polynomial function can be written in the form a(n) x to the n plus a(n minus 1) x to the n minus 1 dot 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 a2x squared, a1x, a0. Basically, you want only powers of x that are positive whole numbers and with coefficients in the front, okay? So if we look at these three functions here, we want to decide which ones are polynomials and which ones are not. So they might not look like polynomials when you very first start, but if you were to do some simplifying on them, you could see that this is just 6x to the fourth plus 4. So polynomial. Same thing with this next one, negative x cubed plus 4x, polynomial. This one, not polynomial. The reason is because we have that square root. There's no way for us to get rid of that square root right there. So that's going to cause us to be not polynomial. Another example you might see is 1 over x, not polynomial. Anytime you put x's in denominators, when you put square roots, all those things are not polynomial. So if you're looking at an equation, you can determine if it's polynomial. What happens if you're looking at a graph? Well, a polynomial graph has two characteristics. It has to be smooth and it has to be continuous. So there can't be any breaks or holes, there can't be any sharp turns. So on the left-hand side here, we see two graphs which represent polynomials. They're nice and smooth. At the top, they have smooth humps. There's no breaks, there's no holes, there's no asymptotes. Whereas these two on the left, look, this guy, he's got a sharp point at the bottom, not a polynomial. This guy's got a whole bunch of broken spots at -1 and 2, not polynomials. So when we talk about polynomials, one way that we characterize them is by using their degree. So the degree is the highest power of the variable. It doesn't have to be at the beginning. We're going to look all the way across all the terms of the polynomial and look for the one with the highest power. So the leading term is the one that contains that highest power. So it's the whole term. The degree is just going to be the exponent. The leading term is going to be the whole thing with the coefficient, the x, and the exponent. And then the leading coefficient is just the coefficient of that leading term. So here are three polynomials. We want to look at each of the terms of these polynomials to find out what's the degree, what's the leading term, and what's the coefficient. So when I look at this first polynomial, 3 plus 2x squared minus 6x cubed, I notice that this guy, the minus 6x cubed, has the highest power. So he's the leading term. So not necessarily in the front, just the one with the highest power, -6x to the third. That means the degree is the exponent, 3, and the coefficient, the leading coefficient, is that number in the front, -6. Okay, so let's try again. 4t to the fifth minus 3t squared plus 7t. So this time it occurs at the front. The leading term, the one with the highest exponent, is 4t to the fifth. The degree is that exponent, 5, and the coefficient is that number in the front, 4. Okay, last example, 6p minus p to the fourth minus 1. So if you look across all of those, the one with the highest exponent is that -p to the fourth. So the leading term is going to be -p to the fourth. The exponent is 4, and the leading coefficient is that negative sign in the front, right? So the degree, the exponent, is the 4. The coefficient has to be a number, so it can't just be that negative sign, but remember, multiplying by a negative is really the same as multiplying by -1. So my leading coefficient is going to be -1.